Okay, now I'm in Grasshopper interface, and let's have a look at the static system and try to understand how many times the system is going to be static indeterminate. It is going to be one time, and how does it depends on the number of the members. So first I'm gonna start with a point with these coordinates, and I'm gonna translate the geometry direction. By default this is z. At this point I'm gonna need also in unit x. Distance is going to be some default value. I need the line from these 2 points, the first one and the displaced one, and the translated one. And then I'm gonna divide curve to be able to connect the other members. So maybe 3 times. I'm gonna shift points because I'm gonna need the last 3. So I need this to be false in order to be able to select only the last 3 points. Otherwise the list will be wrapping. And very quick list item. Okay, I only need the 3 items. And just take a copy from the line, make this point at the beginning with this 10 second, and so I have the system. I'm gonna make the check with 1, 2, or 3 members here. So let's just constrain this up to 4 with 3. Wait for to change this. And from Karamba, I'm gonna need the component line to beam. Oh, here I've forgotten. After I've divided the curve, I need to create a polyline. Between these 3 points. So now I have the polyline on the points, and then explode the 3 parts of this curve. Here I have 3 values. In our formula, it is important that we have 6 members from this system. So the bottom one has to be explode. And now I can collect all of the lines. Feed it into Karamba. Now I can see that I have 6 elements, and the joints, the points are 5. This is what I'm going to need later. And for now, I'm gonna group this. This was the first part. Okay, let's create at first the design, the components of the components that we're gonna need for the analysis in Karamba. This is going to be supports of the main beam and the uh, tension beam, tension members. Second, we are going to add some joints on these members, and because they are also connected to the main beam, and we don't want to extract some extra moments that then which doesn't exist. So I'm gonna need this, and of course our load. This is gonna be some concentrated but block beam load. I'm gonna add this only in beam to see the form of the bearing moment diagram. Throw Let's just collect points. And then with all of this, I'm going to assembling the model, the theory first. This analysis to check if the system is rigid or not. And last, I want to have some mod components. I want to check this. And then for the beam view and different diagrams. Okay, and our main part will be to check if the system is static indeterminate with the C#. This will be our last part. Okay, let's give here first a few names of these beams. For example, like so. Tension members are called A, B, C, and the D will be the main cantilever beam. Let's just connect here. And because after that I want to calculate this moment in ZX diagram. So for the second condition, I'm going to need have. I'm going to constrain the translation of them. And like a hinge member in a simple beam, I'm going to left this one free. Just collect. We already have, so we can see them. What about the joints? The joint is at Karamba 3D at elements. I would say these first elements are the first three indices from here. So I can go out. You can go out the nth element, the fourth one, and I'm left with these three indices. So let's just feed them at elements. Two elements. To geometry, sorry. So I need these 3 points, which I've had shifted here. I can merge them. Our geometry is going to be a point. Here, because I'm working in the plane epsilon x, I want to release, so I want to hinge only in one direction. Let's see how does it work. Okay. And last, I'm going to have straight forward of this beam and say that is going to be a z negative. Float and is going to be minus 10, for example. What happens? Okay, my the visualization of the load. I mean minus z. It's my deformed shape. So here this component doesn't turn red. So the system is maybe indeterminate, but is not rigid for now. Just see the form of the my diagram to make this with. Okay, so now we see we have the moment in the beginning and in which which action with the members, because this tension helps to reduce the moment in the field. So we have bigger moments here, and here we have again the hinge. The thing that we're searching for is the indeterminacy of this static construction. So what I'm gonna need next is here under results, the reaction forces of the model. Okay, what I directly can take out of these components are the reactions of our two supports. So here I have fixed support, but with in the plane xz we have only two members for the reactions for each support, and therefore the zero component is in direction epsilon, which is out of the plane. Okay, now we have this, and also for the moments I can assume that I am gonna have exactly one value different than zero, because this is the moment around epsilon, um, this on the first support. Okay, let's see. And therefore I would like to apply one C# component with a few lines, where at the end, where in the outputs here, we're going to be able to find the indeterminacy. So it is going to be 0 or 1 or etc. And we can apply this rule for all constructions and all static systems. Let me first write simple as text. What are our are the symbols we are searching for? So we're searching for the members, joints, the number, oh sorry, the number of the members, the number of the joints, and the reactions. Maybe you already know this formula. And just rename, I'm going to rename and see what I've already have what I can already use ready from the Karamba interface. Okay, so the reactions, we're going to apply addition to the RF here. This is going to be my reactions. Later on, I'm going to search through the lists to find the values different than 0. And the members, this is easy one, since I already got them from the beam to line component, are over here. So elements, points are from the formula, are my joins. See if I just can take them. So I can take them like just a number, and the same goes for the members. The members are 6 elements, so 1 2 3 4 5 6, as long as we divided the main the beam into uh, three members, let's say. And now I have my inputs and the outputs. So I'm searching for the indeterminacy. I want to collect the members to be able to create this formula, the members, and then the joints. Let's write it out. Reactions. To check what kind of inputs I already have. These are the objects, but I need list of vectors because the reaction forces and the moments are list of coordinates, and it's very like vectors. And the other ones I'm going to left as just list them also because I have list of the members and list of the number of the joins, and the output I'm going to left as reference objects. Let's see. So one right click. This is going to be list access and vector. Also this one. Make as list access and same for this one. All right. So from here, I'm just going to write a few functions. So my goal is to inside of the C# component, I want to collect the number of the members. I want to collect the number of the joins. To make this formula, then I'm going to make this formula inside, and I'm going to take as input the indeterminacy as number also. Okay, and the other ones I collect them only to check if what the current result is. So for example, the members. So for the members, I'm going to make a new list. This integer because it's 1, 2, 3, 4, 5, etc. I'm going to call this members. Also a new list. Like so. The variable m, I just want to make it small m to make a difference from this big one. And I'm going to count the number of the members in this list that I'm inputting here. And I'm going to output my object members as this small m. See what we already have. Yes, I have this already 6 times. Let's go ahead and make the same for the joints. Our joints. On the input list, I count them. I output joints now is this number of joints. Okay, now I have 6 members and 5 joints. Okay, these are going to be included in the formula. So the next component that I'm missing here is a number of reactions that are different than 0, and from the both lists for the forces and the moments, because it can be that the system has no moment or has more reactions that are 0 and so on. So let's see how we can find this. So I'm getting further down and making the next milestone, let's say. So I'm going to collect the sum of the reactions. First, I'm going to make a new list from integers of numbers. So since I gave here the type of vectors of this list, I want to define a vector so that after I defined it, I can get through through x, y, and z, and to search for zeros and to extract the values that are different from 0. So going further, I'm going to need a new vector list. Okay, this is the vector 3D. It's called v. function. Okay, list 3D. Okay, what is going to be in this list? So we know that rf is, I want to count through the components of the rf, and this is a list, and in every index 1 or 0 there is component in x, y, and z, so we can um see this like list of vectors. So this is what I'm saying here. This list of vectors, I'm going to assign component of rf to this list. So for rf, the count of rf, getting through the components of the rf, right, opening this and adding to the new list v, adding each one of the items from the list rf. Okay, and on the place 1, 0 or 1, and I'm defining the components of this vector. 3D, which contains x, y, and z component. Okay, after I define this, I can start to search if there are values different than 0, which are on the place of x, y, and z. Let's see how can we do this. So we need the sum to define the sum, which is some integer number, and I'm going through this list. So the list z. Okay, now I'm using the list that I've defined to collect the sum there. So in this list, I want to collect the numbers which are different than 0. So add to this list first 0, and then add each element which is not 0. So if index I and each x component of this list is not 0, so then add to this list so was this if the y is different than 0, and if the z component is different than 0, add 1. And inside of this for loop, this is the if, this is the if. Okay, so my sum, I want it to be equal to the list of numbers which I've collected here, which are different than 0. And let me just close Okay, so this block here was so far for the list RF, but what about the list RM with the moments? So I would say on this place, I just copy, paste this, and I'm going to change the just few names. So my end result is going to be sum of the numbers from the list RF, which are different than 0, and then the sum of the list RM of the X, Y, and Z, which are different than 0, and then the sum of all of them will give me the reactions, which are different than 0. And with this result, I'm going to go to the formula. I already know the reactions to get my static indeterminacy. So let's see further. So I'm going just straightforward, not think about names, but rename it like numbers 2. This is going to be V2, and this is no more I, but the next letter, let's say K, V2, and here change to introduce sum 2. My second list, okay, make a mistake. All right, so I have the same constructions, and 2 is going to be my numbers 2. Okay. Okay. And here outside of the loop of the for loop, now I need to find my output, which was called React. It's outside of the component C#. It's going to be equal sum plus sum 2. And okay, this is so far for the reactions. I want to check if this is working. No, it's not working. The name I, so I forgot maybe to change it somewhere. Yeah. And of course, yes, this is the name of my list is already RM. Sorry. Okay, now check the reactions. Yes, there are 5 right now reactions. Let's see. So I have 4 which are different than 0, plus 1 moment different than 0. Yes, this gives me the number of 5. Let's see if, for example, I would introduce other moments on the other support. Yes, I have already 6. This is one more on the Y direction. Okay, let's just return how it was. 5. And what is left is to calculate the indeterminacy. Copy this for later. I'm gonna need here like my like my output. Terminacy is 0. And on the formula, this is going to be to the members plus the sum of the reactions, sum plus sum 2 minus times the joints, the number of the joints. And my output is going to be equal this value. and I'm getting the number of 1. So that means that my construction here is 1 time indeterminate. So I'm going to need one more equation to analyze the construction. Um, yes, thank you for watching. I think this is all for now, and just stay tuned for the next video. Thank you and bye.